which some of you know about. So this is about isoperimetric inequality. It is not unrelated to what we are going to do later. So this is so I was planning to skip it. When I teach this course, topics in analysis, I often teach this isoperimetric inequality from a much more general point of view. I don't particularly care for the one that I am doing now, which is nice, but it is somewhat limited. But the reason is that when we go to graphs, it is actually not irrelevant. This is kind of relevant to the what we are going to do. So that's why I want to say this. So when I teach in topics in analysis, usually I ask, now I have already told you the answer. So what is a theorem that most people know, but very few people know the proof of? It is, so my candidate for that is isoperimetric inequality. What is isoperimetric inequality? In 2 dimensions, in R2, it says that for among all bodies with given perimeter, the disk has the maximum value or maximum area. So there is some, so if you are given a length of rope, you are given a length of rope. Let's say it is kind of tied to the end. So you can place it in any way. You can place it like this. You can place it like this. You can place it in whatever form you want. All the land that is inside is yours. So how will you do it if you want to get more land? The best way is to do it in a circular way so that you get the inside the disk. So this is the statement of the isoperimetric inequality. But when you try to prove it, I mean, of course, a lot of things have to be made sense of. So what is a body? What is perimeter? What is area? Okay, so it is, and is it unique? So all these questions crop up. So we will just do a kind of limited situation. So limited sort of thing. So what we will do is, so for us a body here in our limited setting, here a body is a region bounded by a smooth simple curve. Okay, what is a smooth simple curve? So a simple curve is a simple closed curve. So if gamma is a function from the circle to, let's say, R2, continuous and injective, that's what a simple closed curve is. A simple closed curve is a curve from the circle. So it's a mapping from the circle to the plane. So what can it do? I mean, it can map things, but it has to close itself, but it's injective, so it doesn't do things like this. We don't allow this because of the injectivity condition. Okay, so this is called a Jordan curve. So this is what is called a Jordan curve. But we also assume gamma is smooth. We will see how much smoothness we need. So that is gamma of e to the it, we will write as x of t, y of t. Okay, where x and y, say if I use the t notation, so they are mappings from 0 to 2 pi to real numbers. These are periodic and continuous. Continuous means so x of 0 is x of 2 pi, etc. All this is so that is what we mean by a okay, but that is a curve. So where is the body? Okay, so so what is the body? So it is a fact. Okay, so let me state the fact. So fact is, if gamma is a Jordan curve, then if you look at R2 minus the image of gamma has exactly two components. One bounded, one unbounded. Okay, so you can see it. I mean, intuitively, here is the bounded component of this, and the unbounded component is what is outside, right? So this is what we mean by the region enclosed by gamma. This is what we call the region enclosed by gamma. If you have a Jordan curve, then the complement of the image will give you two components. One of them is bounded, and that is called the region enclosed by gamma. It is, by the way, a non-trivial fact. This Jordan curve theorem is a non-trivial fact. But maybe, I don't know if there is a simpler proof if you assume gamma is smooth and stuff like that. Is there? Does anyone know? We are going to just assume it anyway. But does someone know if it is an easy thing if you assume smoothness of gamma? I don't know. So, but topologically, you just need a continuous curve, okay, from the circle. So that's all you need. So this is what we mean by a body. A body for us is a region enclosed by a Jordan curve, a smooth Jordan curve. Okay, that is what we mean by. Okay, so this is what is a region bounded by a. So this is what we mean. The region enclosed or bounded by. So I got there bounded by. So region bounded by gamma. Is this okay? So we will take this for a fact. We won't worry about all these technicalities. So this is the body. Okay, so what is its perimeter? So let's call it. So now another fact is, so this region. So let's call it omega gamma. Okay, so let's call it omega gamma. So this is point 1. So now we can talk about the area of omega gamma. It's just the Lebesgue measure. Of course, you have to be sure that this is measurable. Yeah, so it is measurable. Again, how do you prove that? Is it easy to see? I'm not going to worry if it's not. If I don't see it, I'm going to just assume all this. I don't want to spend time on it. So this omega gamma, the region enclosed by a smooth curve is necessarily measurable. So why is that? I mean, of course, what is the region enclosed? That one has to be clear. Yeah, so there are, if it's a smooth curve, you can do this. Okay, so for smooth curves, I can in fact, yeah, so if it's a smooth curve, okay, I can explain how it is, but also let me write the perimeter of gamma. Okay, so perimeter of gamma, perimeter of omega gamma is by definition the length of gamma, which is by definition integral 0 to 2 pi. You look at gamma dot of t norm, absolute. If you look at it in as R2, then we put a norm dt, which is actually nothing but 0 to 2 pi. So this is the definition. Length of gamma is this. Gamma dot of t is nothing but x dot of t, y dot of t. So the length will be the square and then square root and then dt. This is our definition of length of the boundary. Is this okay? So this is the setting we are going to. This is a somewhat limited setting. One can go much better, but for us, body means the region enclosed by a smooth Jordan curve, and the area is the area of that Lebesgue measure of the enclosed part, and perimeter is what is the length of gamma. So this is well defined. Perimeter is okay. My area is okay as long as you know it is measurable. Is this okay? Yeah, one way when assume gamma is smooth, so we don't need the Jordan curve theorem, I realize. So when gamma is smooth, or even just rectifiable. Okay, we can define a function. Okay, now I am writing in the complex form. Okay, complex numbers too. So complex numbers we identify with. Okay, so we identify R2 with complex numbers here. Then you can define the winding number f of z. You define as 1 over 2 pi I integral over gamma 1 over d zeta over zeta minus z. If you have seen complex analysis a little bit, then you would have seen this. Anyway, what is it defined as? It is defined as 1 over 2 pi I. What is the meaning of this? It just means you take a parameterization. Gamma is a function from t to r2, right? So we write it like that. So we take gamma of t, which is a complex number now, minus z, and d zeta just means gamma dot of t. Now it's a complex number, no norm and stuff like that. It is not, there is no norm. Okay, it is gamma dot of t dt. Is okay. It's a complex number. We identify R2 with complex numbers. So then the fact is you can show f takes only integer values. F takes values. So right. So maybe it is not so obvious. So f takes only two. Okay, I will just assert f takes only two values. 0 and 1. And omega gamma is nothing but the set of z where f is actually 1. Okay. So at least okay. So I don't know if I can quickly argue that this takes integer values. This is called the winding number of gamma z, and without much difficulty one can show this is an integer, and it is piecewise constant actually. So it is piecewise. So if it's locally constant, so it okay. I don't know if Kaushik has an easy argument to say that it takes only two values when it's a Jordan curve. Okay, so I don't know if that is easy, but you have something.
But I mean that only for simply connected, or right? You
No,
have
it's
to,
a Jordan curve, right? I mean, so
yeah.
what is bounded inside by a Jordan curve, it should have two values. So anyway, let's assume this. F takes only two values, 0 and 1. Then omega gamma is by definition the set of z where fz is 1. At least this way you see the measurability of omega gamma quite easily. It's fairly easy that its f is clearly a nice function of z. Okay, for z not in gamma. For z not in the image of gamma.
Sir, can we use the Cauchy theorem?
This is actually, I mean, well, it is more basic than the Cauchy theorem. Yeah.
But Cauchy will directly give if Z is inside the region, then it will be 1, and then otherwise it will be holomorphic and it will be 0.
But no, but that is the point. What is inside? For a general closed curve,
Okay.
for a general closed curve, f can take integer values also. Okay, what I was trying to see was whether I can use this to define the inside. So in that case, you cannot say it's inside, it is 1. Also, where is the 0 and 1 coming from? In general, it can be positive or negative integers. So you have to use the injectivity of gamma to say that it is actually takes only 2 values, 0 and 1. But all these are somewhat intuitively okay. So we understand inside, outside. So let's accept this. Okay. So is that okay? So yeah, but I want to tell something about the area. So now the claim is that now we can state a theorem. If gamma is a smooth Jordan curve, area of omega gamma is bounded by the length. So for a given length, what is the disk that we can get? If there's so the radius is r, then 2 pi r is the length of gamma, right? Okay, so r is that, and then the area is pi into r squared, which is yeah. So if so pi into r
L
squared,
squared by 4 pi, right?
4 pi square. So L square by 4 pi. Yeah, exactly. So it is the length of gamma square divided by 4 pi. So this is the isoperimetric inequality. So this is a limited, as I said, a limited isoperimetric inequality, which is all we will do. Again, this can be done using Fourier analysis. That's why it is nice. So it's a simple application of Fourier analysis. So let's do that. But before that, one small point. So for a length, I gave a formula. For area, I didn't give a formula. So we need a kind of formula to work with it. Okay, so maybe I do that first. So before going to the proof, let me write proof. So we have the perimeter of gamma. So let gamma of t be x of t comma y of t, t in 0 to 2 pi. A perimeter of gamma is a perimeter of omega length of gamma. Okay, whatever it is. So the perimeter. Okay, I already got in terms of length. So let me just write the length here. So length of gamma is the integral from 0 to 2 pi x dot t square plus y dot t squared square root dt. I say that area of gamma, omega gamma, I also want to write a formula for that. So that is going to be 1/2 of x of t y dot of t minus y of t x dot of t dt. So this is the claim. Okay. Well, okay. So with this you may have seen. I mean, if you have seen things like Green's theorem and stuff like that, you probably have seen. Sometimes it's written in the form x dy minus y dx. 1/2 of that will give you the area of the enclosed region. This is the way it is written. Let me just give a very simple. I mean, so is there anybody who has not seen this formula for area? Okay, so let me just give a very simple reason why this is. I mean, this is a very intuitive formula actually. I mean, it doesn't look quite like that, but the point is, if you think of a polygon, okay, so if you think of a polygon, I mean triangle actually. Why polygon? Yeah, so think of a polygon, triangle with let's say u is this vector and V is this. Okay. Now what is this area? What is the area of this? So if you complete it to a parallelogram, okay, so this is U plus V. We know that the area of triangle ZOUV, okay, is 1/2 of the area of the parallelogram. But what is the area of the parallelogram? It is just the cross product of U cross V norm, right? So you know that if you take the cross product, you get the norm. Now that is the underlying point here. So how is that going to give you anything? So think of a polygonal curve, okay, made up of regions like this. So imagine, so you try to break it into triangles. So you make it into triangles and then add up the areas of the triangles, okay? So you have U1, U2, U3, and so on. For each of them, we can use and you can write a formula for the area of a polygonal region. The point is that when U2 is, let's say U1 is U and U2 is U plus H. H is supposed to be small. If you want to approximate, then U cross U plus H is same as U cross H, right? So U cross H, which is U1 H2 minus U2 H1 by definition. So what you have here is precisely that. It is, so this actually gives the signed area, so to be precise, but U1 H2 minus U2 H1 is like, U1 is like X and H2 is the difference in the H is like, this is like gamma of T, or it is X of T, Y of T if you want. And H is like D of that, dx of T, dy of T. It's the infinitesimal difference, so to speak. So H2 is like X dy and U2 is Y and H1 is like Y dx. So that is what we have here, X dy minus Y dx. So that's this area formula. Okay, so we will take this, and once you have this, you just apply Fourier analysis and you will get the answer. Okay, so what is it we want to do? So we now write everything in Fourier expansion. Okay, so yeah, so how do we write? X and Y are functions, so we could write the complex valued function. Yeah, is it better? But then this is, yeah, if I write in terms of the complex valued function, X of T plus Iy of T, is that better? Then how do I write this one? Does anyone see? It is, yeah, maybe
Z bar dz, right? Something like that.
what is it? Okay, yeah, okay. Let me just stick to, let me not be adventurous, just write separately. Xt then also we have x dot of t, the derivative, we know what we get. It's like formally differentiating here. You will get in x hat of n. Again, in y hat of n e to the int. Just one clarification to give here. So here, these expansions are all actually, so because of smoothness, these are uniformly convergent series. So, okay, just to be a bit overcautious, example, if x and y are C3 functions, okay, you don't need, actually you only need C1 here, even less than that, but let's for a moment assume x and y are C3 functions. Then we know that x hat n, y hat n are decay faster than what is it, n cubed, right, or something like that. Something like that. So even with, if you put all the absolute values, you get a 1 by n square here, n by n cube, n by n cube. So all these are summable. But if you are a bit more careful with what we do, you will see that I don't need uniform convergence of these two series. These are in L2 is sufficient for me. Okay, I would like this to make sense. I want this series to be meaningful in L2, and that's all we need. So actually we need L2 convergence of x dot y dot of the series for x dot y dot. In other words, it works even if we assume that gamma dot is an L2 function. That's all we need actually. But let's not worry about that. So let's take it anyway. So once you have this, you can write both these formulas, right? What is x dot t square plus y dot t square? I mean, so how can we write this one? Okay, so that's a little tricky maybe. Is it something I can square root of x dot t square plus y dot t square? Yeah, how do I do that?
Or don't you do the maybe like conjugate kind of things? Can you do that?
No, but there is a square root, so I'm wondering how if it was square, then I would be okay, right? So I want to write it in terms of the Fourier coefficients, right? Is it?
Mm-hmm.
Yeah. So I'm just thinking how I do this. So the length. Yeah. So the usual way it is done is to first reparameterize. Okay, so you can always reparameterize so that x dot y dot always the speed is 1. I mean, so that is what is done. So let me think for a moment. So let's take area of, let me do the second one first. Area of omega gamma is simply 1/2 inner product of x and y dot in L2 of the torus. Okay, actually there is a 2 pi missing, so maybe I put a 2 pi here. Minus y and x dot in L2 of the circle, which we know is actually same as what is it actually? That will give me pi times summation x hat of n, and y dot hat of n will be conjugate. Y dot hat of n conjugate by Plancherel, which is actually y dot hat of n is into minus in. I get a minus here, in y hat of n with a conjugate here over n. And then I get a minus here, and here I will have y hat of n. I get minus in, so that becomes plus in x hat of n conjugate. Okay, so this is what we get by Plancherel. Now, what is that? That is, let's pull out the I should not have been there. Something is missing. No, it's okay because there is an imaginary part. So it is pi times sum over n in into. This is cancelling. Yeah, sorry, no, in x hat y hat bar minus y hat of n x hat of n bar. Okay, so it's actually 2 times the imaginary part of that. So this is going to be positive number, no doubt. So, but we can put absolute values inside. So the area is going to be less than equal to pi times sum over n. We can put all the absolute values here. So absolute
No, the
value.
sign changed. No, from this there is still a minus outside.
Okay. So there is a minus plus. Okay. So you're right. So y hat x hat bar minus, yeah. But I'm going to put absolute value now, and this one I use Cauchy-Schwarz to write that it is bounded by x hat n square plus y hat n squared Is that okay? Because this is just this is AB plus CD. So you write as A square plus C square B square plus D square root. With both of them are equal, so you have no square roots here. So you get this. This is the bound on the area. Is this okay? So what about the length of gamma? The way we do is, so what we, I mean, so the easiest way I can see, because I have a little bit of trouble figuring out what is the square, how to do the square. Without the square root, this would have been again Plancherel, right? Without square root, this would have been Plancherel, and I could have x dot square is sum of n squared x hat of n square. Y dot square is sum of n square y dot of n square. So that would have been easy, but that's a little yeah. So the way to do it
Isn't
is,
there
so
a 4 here?
sorry.
Isn't there a 4 there after you apply Cauchy-Schwarz?
No, I am applying Cauchy-Schwarz on. No, it is just x hat of n minus x hat of n y hat of n inner product with y hat of n x hat of n. I'm just doing the dot product of these two bivariate vectors, and the norm squares are both equal to this. There is no 4.
Yeah.
Yeah. So what we do is, okay, I don't know if this is a necessary step or is there some trick to computing this, but without loss of generality, I should have done this before. We can reparameterize curve, reparameterize gamma, so that gamma dot is a constant. Is constant. See, you have a running track. This is the image without loss of generality means, what I mean is without changing the length of gamma or area of omega or the region itself. See, the thing is, you have a track. Gamma is like a track. You can go at any speed around it. You can always run at uniform speed. So we can do that. Gamma dot of t is constant. We can do. So in that case, so let's say this constant is some c. The length of gamma is going to be 2 pi c on the one hand, because okay, so length of gamma is actually the integral of 0 to 2 pi square root of x dot of t squared plus y dot of t squared dt. But on the one hand, this is c, it's a constant c times 2 pi. Yeah, so what? I mean, yeah, so that is the length. But I still need to bound this. Hold on, I'm confused. So this is
Can we differentiate x dot t squared plus y dot t squared or something? Just since that's a constant.
no, this sum is a constant. What we can, another way to write it is, since this is always constant, so this is always c. So what trick I will use is that this is actually equal to, I can pull out a 1 by c and write it as 0 to 2 pi x dot of t square plus y dot of t square dt. Is it okay? Because c is actually, this is always the constant c. Okay. So I can pull out 1c. I mean, the square root is the constant c. I pull out 1c and then put the square here. This works. Now this works. So now this becomes 1 by c times. Now we can use Plancherel again. X dot t square will become n square x hat of n squared. And this becomes n square y hat of n squared. Okay, I should put absolute values here. Over n in z. Is this okay? I mean, this is a trick, but it is good. Okay. So we get that this is equal to C2 pi. So what we have is equal to so the length is 2 pi C. So let's write it as length times C. So this is actually length into C, which is again length square by 2 pi. Okay, so we can write it as length square by 2 pi. Is that okay? I made one, yeah, so this is fine. So now how is this bounded in terms of this? So how do you bound area in terms of this? This is, of course, n is yeah, so the 0 term can be ignored in both cases, right? So for all other n is at least 1. So this thing we can write as easily bounded by the square. Pi times okay, so that is a slight problem now. So what I am getting is that this is actually, hence we are getting that area is bounded by this quantity here is what I have written as length square over 2 pi. So I am getting length of gamma square over 2 pi square. I should have gotten 4 pi square. Some 2 is missing somewhere. I have to worry about that. But this is the idea. Is this okay? I mean, overall idea. We have to fix the 2 still. Maybe Somendu, you had the point somewhere. Did I lose a factor of 2 here?
No, that's correct. What you did is correct.
Huh?
No, that what you did is correct. That's this is what
Okay.
you did.
So then now why is it? I should get 4, right? So I included the factor of half in here. Yeah, is this correct? The Planchagel, am I missing a factor of 2? No, this one with the 1 by 2 pi, I'm okay, I guess. So this should be okay. So I get pi. Okay, sorry. Here also there is a 2 pi. This x dot square, I forgot. In this Planchagel, there is a 2 pi. Okay, so there is some missing things. In fact, I should not get pi squared either, right? So there is a mistake. So if you remember, what I should get is length square over 4 pi, not pi squared. So the mistake is here when doing this integral, I wrote it in terms of the coefficients, but it is 2 pi by c, right? Because it's not dt over 2 pi. It's so with dt over 2 pi, I would get this. So it is this. Because of that, what we get is this is actually equal to just c. Yeah, this is not L square by 2 pi. What I get is this sum 2 pi cancels. This is equal to c squared, which is L squared over 4 pi square. So I get pi in no, even worse.
Yeah. No, but there is
So
a
you
pi
have a
on
pi
top.
factor outside.
Pi cancels. There's a pi on numerator, no?
Sorry.
Area less than pi times something. So there pi
area
times.
less than pi times. Okay. Area less than pi times this by 4 pi square, which is L squared over 4 pi. Okay. Thanks. Yeah, that's correct. So there is an extra pi. Okay. So this is exactly the isoperimetric inequality. Is it okay? I mean, any questions, comments on this? I thought I will finish it quickly, but I forgot some of the tricks here. But any questions here? It's a nice application of Fourier analysis, except that really you can go much more powerful in isoperimetric inequalities. You don't need this much regularity of the region and all that.
Sir,
Yes.
in this proof, didn't we like preclude all those shapes with sharp edges up front, like polygons and all, because of the smoothness or something?
That's right. But if you look at it carefully, where to use Planchagel, I don't need things to be in uniform. So here, what I need is x dot y dot have to be L2 functions. Okay. And then you can include sharp ones also, no problem. X dot y dot should make sense. So what will this work for? This okay. So there are two possibilities. Here you assume this way. Okay. So now you can either do two things. One is you can try to rewrite this proof assuming very little about x dot y dot. If you assume x dot y dot in L2, you should be able to prove. You can, I mean, I don't see this written in books, but can we go more general? So now suppose gamma is a rectifiable Jordan curve, meaning it has length. So, okay, if you, for example, piecewise smooth is okay. That's what you are worried about. But rectifiable is more than that. It need not be piecewise smooth, but if you want, you assume piecewise smooth. Okay. So what we can do is in a small, you can, if I fix any epsilon neighborhood of this. Okay. I can certainly find a smooth Jordan curve, which is inside this yellow region. Okay, something that is smooth. Okay, this yellow region is supposed to have uniform thickness. It doesn't look like that in my picture, but okay, so what I'm saying is that find gamma n, which are smooth Jordan curves, such that gamma n and gamma image, let's say, image gamma n is contained in, let's say, 1 over n neighborhood of image gamma. This width is supposed to be 1 over n, and vice versa. You understand? This is called Hausdorff distance. You can find a smooth Jordan curve. Smoothness is easy, right? If you have a triangular region, you just smooth it a little bit here. There is no problem. You can approximate it by smooth ones. So then
it's 1 o'clock.
2 points. So then my claim is so twofold. Area of omega gamma n should converge to area of omega gamma, and length of gamma n, it need not converge to that, but liminf is greater than equal to, oh sorry, in the end the length can increase. The lim sup of the length is smaller than, sorry, no, it will go the other way, right? I see. No. Sorry, what I was thinking doesn't work. You can approximate it, but you want a. Yeah. So you. Okay. So the thing is, okay. So I thought something wrong. This won't work. This won't work. Okay. So what you want to do is you want to find an approximation so that this both will happen. Length of gamma. If you can manage that, I think it is possible. It should be possible, but once you manage that, then you get the isoperimetric inequality for that. So because area of omega n is bounded by length of gamma n squared over 4 pi, so that will imply for all n Hence, the same for omega. So, for example, triangles and so on, you can easily see that you can manage this, right? You just go on this straight line, only at the end you turn a corner smoothly. So you can get those things from here. You can see that the length of this curve will go to the length of the perimeter of triangle and area inside will go to area. So you will get those things also. So instead of trying to fix here to go maximal generality, you can use this and approximate to get some more. And I think you can go as far as rectifiable curves, but I won't bet my life on it. Okay, so I will stop here. Any other questions, comments you can mention.